All right, how is everyone doing today? Good? Not good? Oh, I'm sorry. Do you have a good weekend at least? Yeah, all right. Okay. Does anyone have any questions before we get started? Cool. All right, let's continue our stereochemistry topic. So we were looking at this example where we had said that we need to remember that the presence of a dash or a wedge does not mean I have a chiral center. And that was our last example where we needed to make sure that we're paying attention to the fact that you need 4 different groups to get a chiral carbon. So you have to figure out what are the 4 things attached to that carbon, and they have to be different in order for it to be chiral. So just because you have a dash or a wedge does not mean that it's chiral. It's a good indicator, but it doesn't mean that it's chiral. Likewise, the lack of a dash or wedge does not mean that it is achiral, not chiral. And we had this example where you had 3 chiral centers with no wedges or dashes because we had 3 carbons that had 4 different groups attached to them. What it means when you have that line is that you have exactly a 1-to-1 mixture of your wedge and your dash. So for this molecule, I only have the 1 chiral carbon. This is going to make it easier because there's only 1 to worry about. So there's going to be 1 wedge and 1 dash. So this molecule is actually being represented, or represents rather, a mixture of the enantiomers. It represents that 50% of it is a wedge, 50% of it is a dash. That's what it means when you have that line there. The maximum number of stereoisomers possible is known using this formula 2 to the n, where n is your exponent, and n is the number of stereocenters, the number of chiral atoms that you have. So for example, with that molecule, n is 1. So the number of stereoisomers is 2 to the 1, which is 2, which makes sense because we drew the 2 stereoisomers, the one with the wedge, the one with the dash. So if you're trying to figure out how many stereoisomers, you can also just draw them and then count them, or you can use this formula of 2 to the n, where n is the number of stereoisomers. To know which stereoisomer we have, we're going to need an absolute configuration. So Kahn, Ingold, and Prelog got together and made up this arbitrary set of rules that everyone just went, yeah, sounds good to me, to assign R and S. So what we're going to do is when you have the lowest priority on the dash or back, when you connect 1 to 2 to 3, you're going to have it be clockwise, you will be R. If you are counterclockwise, you are S. R stands for rectus, S stands for sinister. This comes from the fact that back in the olden days, they believed that anything that was left-handed was evil. That's the S of sinister, is like of the devil. We obviously now know that that is ridiculous. And yeah, that's just, I have no other word than it's just absolutely ridiculous. So we can just kind of laugh at it. But that's what the S comes from. So if nothing else, I think that helps you remember S is just a bunch of old guys were being really, I don't know, ridiculous. But S is going to be that counterclockwise, that left-handedness. R is rectus, that right-handedness. Rectus meaning right, correct. So yeah. Being clockwise. So what that looks like is if I'm assuming these are the priority assignments, I have 4 on the dash. So the lowest priority is on the dash. When I connect 1 to 2 to 3, skipping over 4, I'm just connecting 1 to 2 to 3. That is clockwise. So I always kind of have to go, like I look down at my page and then I put it up to imagine that like I'm pointing at the actual clock in the room, like pointing at the actual, like how a clock goes. And then I'm like, oh yeah, that's clockwise. That is R. If when you connect 1 to 2 to 3 with your lowest priority on the dash, and it is counterclockwise, then that is going to be S. The priorities are based on your atomic number. So the higher the atomic number, the higher the priority. The lower the atomic number, the lower the priority. So hydrogen will always be our lowest priority because it has the lowest atomic number. You're going to go atom by atom until you find the difference. So this is the same set of assignments that we used for cis and trans and E and Z. It's just that now I have 4 things that I'm comparing simultaneously. Instead of just doing the left side of the double bond and the right side of the double bond, now I'm doing all 4 things at once. So when I look at this carbon, I'm going to say, all right, the 4 things that are attached are that methyl, the alcohol, the hydrogen, and the ethyl. Those are my 4 things that are attached. But I go atom by atom to try to find the highest priority. So when I just go atom by atom, the atoms that are connected are the oxygen, the hydrogen, the carbon, and the carbon. Those are the 4 elements directly connected to that central carbon. So that oxygen automatically becomes number 1. It is that highest atomic number. So it automatically, that whole group now becomes highest priority. Hydrogen has the lowest atomic number, so that automatically becomes number 4. And everything, well, there's nothing attached to hydrogen because hydrogen can only make 1 bond, but that whole grouping becomes priority number 4. Carbon and carbon are the same atomic number. So I have to walk out another set of atoms in order to figure out where the higher atomic number is. The carbon on the left has 3 hydrogens attached to it. The carbon on the right has 2 hydrogens and a carbon. So that's where I finally see this difference in atomic number. The second that you get to the highest atomic number, that is when you're like, cool, that is going to be higher in priority. So that forces that carbon chain on the right to now be priority 2. The carbon chain on the left is priority number 3. So that makes this 3, that 2. When you're looking at carbon chains and there's nothing attached to them, you can go off of, all right, the bigger group is going to be higher in priority as opposed to the shorter carbon chain. I just caution you that that's not a perfect system. Like that only works as long as there's nothing attached to it, as long as it's just a hydrocarbon chain. Because then you're just like, all right, well, when do I get to the next carbon atom? I'm gonna have more carbons over here, so that works. If I had an alcohol coming off of the carbon on the left, even though it's a shorter carbon chain, it would have been higher in priority because that would have come to a higher atomic number first, right? So it's best to go atom by atom. Just be careful of, I have a lot of students that want to take that shortcut of, well, it's a shorter chain, longer chain, and that will work as long as it's hydrocarbons. I just caution you that the second you get anything coming off of it, you got to make sure you're going atom by atom to find the higher atomic number. All right, cool. So now, this has the lowest priority on the dash. So when I connect 1 to 2 to 3, this is going to be clockwise. So that is R, is that assignment. If I wanted to name this molecule, that stereochemistry goes all the way out front. So if I were to name this molecule, it would be R, and we put it in parentheses, hyphen, no, we're butanol, butan to all. The stereochemistry goes all the way out front. If I had multiple stereo centers, I would put the number right next to it. So if there was like a 2R3S or something, then that would have been how you would do it if multiple. Do you have a question? No, you're perfect. What's up?
So if both of those carbons at the bottom that are labeled 3 and 2 right now, if they were both CH3s, how would we kind of...
That's a great question. Okay, so if both of these are CH3s, how would I change the priority? Yeah. That's exactly right. It's not chiral because now I have two of the same groups. So if you can't assign that priority, you immediately know you can't use R and S because now there is no difference in the priority ranking. It's not chiral. So that's a really good way to kind of double check yourself is if you get to a point where you're like, there is no difference, like they're the same priority level, immediately you can go, that's not a chiral center. I'm not able to use R and S. Yeah, it's a really good question. Your double and triple bonds are going to count as if you have two bonds to that atom. So when I look at this next molecule, and I'm looking at the different attachments, I have an oxygen, a hydrogen, a carbon, and a carbon. The oxygen, again, is the highest atomic number. It immediately becomes number 1. The hydrogen is the lowest atomic number. It immediately becomes number 4. The carbon on the left is going to count as if it has 3 oxygens attached to it because the double bond is going to count as 2 bonds to that atom. So when you're considering what are the 3 things coming off of it as you walk out from that central carbon, you're going to say you have 3 oxygens. On the carbon on the right, we still have the 2 hydrogens and the carbon, the 1 carbon. So the second I got to 1 oxygen, that's going to be a higher atomic number than hydrogen and carbon. But having 3 oxygens, definitely highest. That makes that 2. And then now my ethyl chain is 3. So now when I connect 1 to 2 to 3, skipping over 4 because I just need 4 on the dash, I am now counterclockwise. So I'm now S. So how would you name this molecule? Any ideas? Let's try to get as much partial credit as possible. All right. First of all, we know the stereochemistry, right? So if nothing else, put down an S, and that'll most likely give you 0.5 points, half a point. Cool. Right away, getting some partial credit. You got something down. All right. What is the longest carbon chain? How many carbons? 4. So what is my root? Bute. So if nothing else, if I put bute, and what is the bonding between them? It's all single bond. So what is my parent functional group? Alkane. So I would have butane or butane. That would get me another half point. So right away I'm like, cool. Now I have, even if I'm missing the primary functional group, my secondary functional group, I'm getting something. I'm still putting something down, so I'm still getting some partial credit. Yeah. You are so close. So you have 2, and then what is the word that goes there? What's the prefix for that group? Hydroxy, yeah. So you had the number of the location saying where it went, but you didn't say what it was. So yeah, it is S2-hydroxy butanoic acid. And the way that I normally assign partial credit is that it's usually, like this would have been a 2-point question, and it would have been for having the oic acid recognize the primary functional group, would have gotten you a 0.5 point. Recognizing the root and the parent functional group together, getting the right backbone gets you another 0.5 point. Recognizing the 2-hydroxy, having the locant, the number, and the prefix will get you the other 0.5 point. And then having the stereochemistry would get you the other one to get the full 2 points. That's normally how I assign partial credit on an exam. What's up? If you put a 1 oic acid, that's totally fine. So on an exam, I accept that, even though like the ones can be assumed. I'm all right with that. I'm also okay if you put the E in there. That's fine too. I accept it. You're being more explicit than what's necessary, but that's fine, because that tells me you definitely know how to number this. So I'm all right if you put the 1. It technically is not necessary, but on an exam, I would absolutely accept it. And same thing with the E. If you keep the E there, that doesn't change the identity of the parent functional group. So if you want to always keep the E, cool. It's just, for grammatical spelling sense, you shouldn't have the double vowels, but like I don't care about that. What I do care about, where students do lose points, is if you drop the N, then that makes it wrong, because then you haven't identified the correct parent functional group. So you need the AN, EN, or YN. That N is necessary. So sometimes students drop too many letters, and then that gets really wrong. So you want to make sure that you have the but, the AN, with or without the E, and then the oic acid. Any other questions about that? Yeah. So if you have a triple bond, then it would count as 3 bonds. So if I had that nitrile there, then it would be as if I had C 3 bonds to N, and then the other carbon was still 2 hydrogens and 1 carbon. So it would still be 1, 4, 2, 3. So that would still be S. Yeah, this one was just, because it was a carboxylic acid, I had 3 bonds to oxygen anyway. But if it had been a triple bond, we count it the same way, as if it's 3 bonds to that atom. What's up? Yes, that carbon is carbon number 1. Your primary functional group is always going to be included in the backbone. The carbon of your primary functional group gets included in the backbone. Any other questions? All right. So these were the same rules that we had for cis and trans or E and Z. For our alkenes, the difference is we are comparing all 4 simultaneously to each other. We're ranking 1 through 4, whereas with our cis and trans, it was just high and low. It was you did one side of the alkene and then you did the other. So let's actually do one quick example of that to reinforce that. So for that molecule, would it be cis, trans, E, or Z? Not cis. Yeah. Yeah, it's E. So to assign that stereochemistry, we consider one side of the double bond at a time. So I'm just going to look at the left side, and I'm like, all right, the two elements coming off of it are carbon and a hydrogen. Carbon is a higher atomic number, so that means that carboxylic acid automatically becomes high because of the carbon. The hydrogen is low because it's a hydrogen, it's a lower atomic number. Then I look at the right-hand side. Now I'm disregarding the whole left-hand side. Now I'm just comparing the right-hand side. I have carbon versus carbon. Those are the same, so I keep walking out atom by atom until I find a higher atomic number. Off the carbon on the top, I get oxygen, hydrogen, carbon. Carbon on the bottom is hydrogen, hydrogen, carbon. So getting to that oxygen makes that the high priority versus low. When you connect the dots going through the carbons of the double bond, my highs are on opposite sides. So that immediately narrows me down to either be E or trans, because the opposite. It cannot be trans because I don't have exactly one hydrogen on each side of the double bond. It is not a 1,2 disubstitute alkene. It's tri-substituted. I have 3 non-hydrogens. So immediately that discounts that trans, and that's what makes it E. Cool. That's what I mean by it's the same rules of going atom by atom until you find the higher atomic number. It's just that for your double bonds, you only do one side at a time to get a high-low. Our chiral atoms, we compare all 4 simultaneously to rank the 4. You want to practice naming that thing too? Yeah? Okay. Go ahead. You get E, 3-ethyl-4-hydroxypent-2-ene-oic acid. How many chiral atoms are in this molecule? How many? There are not 3, not 2, 1. There is 1 chiral atom. So remember, anytime you see sp2, it can't be chiral. It has to be sp3 in order to be a chiral atom. So that takes away all of these. Then our CH2s and CH3s can't be chiral because they're going to have 2 or 3 of the same groups. So the only one is this one where I get my alcohol. the implicit hydrogen, the methyl, and then the whole left side of the molecule. Those are 4 different groups. So carbon 4 is the only chiral atom. Why don't I assign R and S for 4 if it's chiral? What's up? So the E is talking about the alkene stereochemistry. So why don't I have to account for the stereochemistry of the carbon, of carbon 4? Go ahead and try. Try to assign R and S. Can you assign R or S? You shouldn't be able to. So why can't I assign R or S here? Yeah. So it's definitely chiral, so we don't have the same groups. So there is, when we look at this, we have oxygen, hydrogen, carbon, carbon. And then if I'm walking out, I would get 3 hydrogens. And here I get carbon, carbon, carbon. So there's definitely a difference in the priority rankings. Yeah. Yeah, we don't know if it's dashed or wedge. I don't have any wedges or dashes, right? So I don't know if my lowest priority is on the dash. I don't know if it's on the wedge. I don't know where any of these groups exist in space. Because when it's on the line, it means half of them are wedged and half of them are dashed. So if I can't assign it, then I can't write it. If I can't assign the R and S because I don't have a wedge or a dash, I can't write in the letter R or S, right? So I need to see that absolute assignment of a wedge or a dash to know if I get the absolute assignment of R or S. What if this, actually let's change this molecule. What if this is a wedge? Now what would we do? Yeah. Yes, it's S. So it would be 1, 2, 3. Hydrogen is the dash. If the alcohol is the wedge, remember if you have a wedge, you have a dash. So that means that the implicit hydrogen must be on the dash. So if the alcohol was on the dash, then that would mean the hydrogen was on the wedge. Because we get 2 lines, 1 wedge, 1 dash. So when I connect 1 to 2 to 3, that is going to be counterclockwise. So that would make it S. So when I would be naming this, what I would do is instead of just having E, I would say 2E 4S is how I would change that name. I would put the location directly next to the letter. Why we don't use hyphens here, I don't know. You just don't. This is the only time that you don't have a separation of your letters and numbers is with the stereochemistry assignment. So it's 2E, 4S. And it's just in order of the number, increasing order of the number locations. Yeah. So it's always chiral. Carbon 4 is always chiral because it has 4 different groups. We just couldn't assign R and S unless I know where the wedges and dashes are. So when it's just a straight line, then I can't assign R and S because I don't know what's on the wedge or the dash. So I can only assign the letter R and S if I know what's the wedge and what is the dash. I have to know that absolute assignment. I need to know exactly where everything is to give it the letter R or S. But it was always chiral. Cool. Any other questions about that? Sweet. All right. So what if our lowest priority isn't on the dash? What if what do I do then? Well, we have a couple of different options. And I want you to do whatever actually works for you. Do whichever strategy gets you to the correct answer, that's the one to do. These are all equally good. So just take whatever one gets you to the right answer. The first thing that we can do is if your lowest priority is on the wedge, then it's going to flip your assignments. So it's just flipping it from dash to wedge, flips the R and S. So now, when my lowest priority is on that wedge, when I connect 1 to 2 to 3, that clockwise is now S. The counterclockwise is now R. And it's just because the lowest priority is on the wedge. So if you flip from dash to wedge, you flip the R and S. You can also rotate the structure. Rotate it to make the lowest priority be on the dash again. Just put it there. So what I think is easiest in order to rotate the structure is I'm going to hold one of my atoms steady, and I'm going to hold one of my lines steady. So I'm going to imagine that I am gripping the molecule, and I'm just going to rotate it so that I'm just like turning the other 3. If you change the other 3, that retains the stereochemistry. So you're just going to hold one line steady and then imagine that you're spinning it like a top. So if I hold this line steady, I chose this line because my lowest priority was the other line, so I knew I wanted to rotate that other one. So I'm going to hold that line steady, and now I want to get my lowest priority onto the dash. So I'm going to push, the line goes to the dash. I can't just flip 2. It needs to rotate. I need to affect 3 sites. So that means that the dash is going to get pushed over to the wedge, and then the wedge gets pushed down to the line. I need to just shift 3 things 1 spot over. So the line went to dash, the dash went to wedge, wedge went to line. I'm just spinning it like a top, where I'm holding line 3, priority 3 steady. Now my lowest priority is on the dash. So now when I connect 1 to 2 to 3, I see that that is counterclockwise, and so that is S. Now it's easier to see that that is S. Rotate the structure whatever way makes it easiest, whichever way gets you to have the lowest priority on the dash. So here, I can hold, again, in this case, I could hold either one steady. It doesn't matter because now my lowest priority is on the wedge. So I could just imagine it's the flipped one, but let's say I want to rotate it. That's where I feel most confident, is when the lowest priority is on the dash. Cool. Now I'm going to push that wedge to the dash. The dash will go to the line will go to the wedge. Everything just takes 1 step over. So wedge went to dash, dash goes to line goes to wedge. And now when I connect 1 to 2 to 3, I see that that is clockwise, so that is R. It is always R. Starting out, it was R. Starting out, the top one was S. All I did was rotate it. I didn't change the stereochemistry of that atom. I just rotated the molecule. Go whichever direction gets you to the lowest priority on the dash faster. So if our lowest priority is on the dash, clockwise is R, counterclockwise is S. If our lowest priority is on the wedge, so I flipped it from dash to wedge, I flipped the R and S, or I can actually rotate the molecule to get the lowest priority onto the dash. And so I'm going to hold one of my lines steady and rotate the other 3. The last method that you can use is one is known as the right-hand rule. And you could also, if you are left-handed and you prefer the left-hand rule, even if you're not left-handed, I actually will sometimes do either right-hand rule or left-hand rule, depending on if my elbow gets in the way or not. So both of them are equal. But if you are doing your right-hand rule, the way that you're going to assign it is your thumb will be your lowest priority. Your fingers will start pointing at the highest priority. So your thumb is low, fingers high. Your palm is your central carbon atom. Then if your fingers can go to the second highest priority, if your hand naturally curls to the second highest priority, that is R. If your right hand curls, that is R. If you have to break your right hand to get to priority 2, you are S. So if you have to turn your right hand the opposite way, then you are S. If your hand curls, then it is R. The left-hand rule is the exact same thing, just the opposite direction. So for left-hand rule, if your left hand can do the curl, then it's S. If you have to break your left hand, then it's R. So right hand curl R, left hand curl S. So what that looks like Ooh, too much. Okay, so my thumb goes along the lowest priority. So my thumb is going to be along this line. My fingers point towards the highest priority. So that means that I am pointing into the plane. My hand naturally curls down towards the line. That means that this stereo center is R because it curls down. If I tried to come out of the plane, then if I had to go backwards, then that would be S. If I'm doing the left-hand rule, I am still, thumb is lowest priority, fingers are highest priority. You can think about it as like there are more of them, so more of them to point towards the highest priority. So you still have thumb goes to the lower left, your fingers point towards the upper right, but going into the plane. To get to 2, my left hand would have to break. It naturally is curling out of the plane. It naturally is curling to 3. So that means that this has to also be R because my left hand doesn't get to 2 first. It gets to 3 first. Right hand can do it, so then that makes this R. It's R no matter which one you do. But right hand can curl R, left hand can't curl R. When we do the other stereo center, oh, I'm too far. That's fine. Okay. Lowest priority, again, thumb is going to go to that line. Oh, I'm not quite tall enough. Then my fingers are going into the plane. No, where's 1? 1 is coming out. So I am pointing out of the page. Now, where my right hand naturally curls, it naturally curls into the plane. So that means that this, in order to get to the line, I would have to break my right hand. That makes this S. If I want to do it with my left hand, my thumb is going to go along that line. My fingers are pointing out of the plane to 1. And now my left hand naturally curls out of the page and down to 2. So now my left hand can get to 2. So that makes this S. I would have to break my left hand to go into the plane. It naturally curls down to the line. It sometimes is easier if you are using a model kit to start to see what it actually looks like. So let me stop sharing this. All right. So looking at this, let's say for this exact structure, I'm going to say white is going to be 4. I'm going to say black is going to be number 1. My blue is going to be number 2. My green is going to be number 3. I probably should have actually done it pretending that they're real atoms, but whatever, it doesn't matter. These are arbitrary assignments for the arbitrary colors, right? So what I'm going to do is I said white is priority 4. So then my thumb is going to be aligned with that bond with the white atom. Then black is priority 1. So my fingers are aligned with that top priority. Now, when my hand curls, it curls to 2, or curls to the blue one. I don't remember what I made blue. Blue is 2. My hand curls to the blue, so that's how I see that that is going to be R, because my right hand can do it. Whereas if I try to go the other way, then it would break my hand. So if I'm imagining that I'm starting out like this, where I have that white on the wedge, black is on the dash, blue is to my left, green is to my right, my thumb is still aligned with that lowest priority. My fingers are aligned with the highest priority. And I'm just trying to imagine my hand curls to the left side to tell me that that's R. That's what you're trying to do on paper, is you're like, all right, my thumb is pointing out, my fingers are pointing in, my hand curls to the left to blue, and I said blue is priority 2, right? That's how we're doing the right hand rule. If you're doing the left hand rule, you do exactly the same thing. It's just that now to get to 2, I would have to break my left hand, right? Whereas it naturally wants to curl to the green one. Cool. Does right hand rule make sense? It's usually something you need to practice. The benefit of the right hand rule is it doesn't matter if your lowest priority is on a line. That's usually the only time you'd want to use it. Most students, if the lowest priority is on the dash or the wedge, do clockwise, counterclockwise. It's when your lowest priority is on the line, that's when it can really help you, because now you don't have to rotate the molecule. I inevitably always would accidentally invert the stereochemistry when I would try to do the rotation. I wouldn't do the rotation correctly. And so then that's why the right-hand rule really helped me. If you're really good at rotating the molecule and that gets you to the correct answer, keep doing that and you don't have to worry about the right-hand rule. Do whatever gets you to the correct answer. So before we move on to chiral molecules, let's do some practice. Oops. All right. Assign R and S for every stereocenter in each of those molecules. Use whichever system gets you to the correct answer the fastest. Whenever you think you have some answers, go ahead and compare to the students near you. See if you have the same answers. Yeah. Oh, yeah. D is deuterium. That's our isotope of hydrogen. It's hydrogen with an extra neutron. So it is going to be a higher priority than hydrogen, because when you do atomic numbers first, and then you do atomic mass as a tiebreaker if you're looking at isotopes. All right, what did we get for the first one? I think I got R. So what is our highest priority? The nitrogen, that amine, is going to be 1 because we're comparing hydrogen, nitrogen, carbon, carbon, right? When you go atom by atom. So the nitrogen is going to be the highest priority. Hydrogen is going to be our lowest. Then we're going to compare those carbon atoms. When we walk out from those carbons, the carbon on the left has 3 carbons attached to it. The carbon on the right has 3 carbons attached to it. So right at this point, you might be thinking, ooh, is it still chiral? And then don't forget the big picture. One's benzene, one's a terbutyl. Those are definitely 2 different things. So then you walk out 1 more level. When you go out from the carbon on the right, all of these are going to get hydrogens. We have 9 hydrogens attached to the substituent on the right, on that terbutyl. On the left-hand side, we get carbons. So off of that carbon, I get carbon, carbon, hydrogen. Down is going to be a carbon, well, it kind of gets messed up with the double bond. It's essentially a carbon, carbon, hydrogen again. The big picture, or the significant point of this, is that I get to a carbon, whereas the other one ends in hydrogen. So that's going to have a higher atomic number. So that's 2, this is 3. So when I connect 1 to 2 to 3, that is counterclockwise. However, my lowest priority is on the wedge, so that flips it, because I flipped from the dash to the wedge, that flips my assignment. So now counterclockwise is R. If I were doing the right-hand rule, I would have my thumb along with that hydrogen. My fingers are pointing towards the nitrogen going in, and my hand will curl to the left towards that benzene. So the right-hand rule also reinforces that that is R. Doing the left-hand rule, I would have to break my left hand in order to get to benzene, so it's still R. All right, what do we have for the next one? The next one, my highest priority is going to be fluorine, then the alcohol, then deuterium, then hydrogen. So when I start out, it is going to be, my thumb is down to the right, my fingers are pointing out at me. My hand is going to curl towards the line before it goes into the plane. That is also R. How about the next one? I'm pretty sure it's also R. So the highest priority is going to be iodine because it has the highest atomic number, followed by bromine, then chlorine, and then fluorine. So I'm going to have my thumb on the right-hand side. This is where the left-hand rule is probably easier because my elbow is getting in the way. So my thumb is to the left, my fingers are pointing to the right, and then where my, oh no, you're right, that is S. Where my fingers go into the plane, that has to break my right hand to get to number 2. So yeah, I'm gonna do the left-hand rule. So when I do thumb is to the left, fingers are pointing to the right, my left hand naturally curls to 2, so that is S. So the left-hand rule was a little more natural that time. For our bicycles, it is usually easiest to just do the clockwise counterclockwise because it's harder to see like what is the wedge or what isn't, because it's like I only was assigned 1 wedge and 1 dash. So when I assign these priorities, the hydrogen is always going to be number 4. My CH2 is going to be 3. Then I'm going, all right, this carbon has 2 carbons and a hydrogen. This carbon has 2 carbons and a hydrogen. So I have to walk out again. Then I get to, well, we're out of time. We'll do this, we'll start with this one next time. Go ahead and try to prove to yourself what the stereochemistry is for that one. All right, have a wonderful day. What's up?